Hey guys, today we'll be trying to solve this question over here. This is a question that I found from Pathfinder through a YouTube video, and I thought it has a pretty neat concept and it's quite hard to solve. So I hope you guys will learn something new in this video. So what the question says is there's a disc over here and it's connected by a bunch of strings. I've drawn the strings with the pencil, right? There's one string that passes through the middle and is connected to like a spring block system, spring pulley system, and another one over here, but it's the same string throughout, right? And there's another string over here, and this string over here is also connected to like a spring block system and goes all the way till here. So of course it's quite noticeable that the two strings are independent, they're not connected in any way, and also it looks quite shabby to see a string over here, I mean a spring, and so let's just tidy the diagram real quick. So basically what I've done here is, since these two springs are in series, we can use the formula 1 over k effective is 1 over k effective is equal to 1 over k1 plus 1 over k2, right? So using this formula, since these both are in series, you get 1 over 2k plus 1 over 2k. This results in like a single spring which has a spring coefficient of just k. And similarly here it's 6k and 12k, they're in series, they give a resultant of 4k. And similarly these two are also in series and the resultant is going to give you a spring constant of just k, as shown over here. And this one, it's connected to another pulley, so we have to deal with it separately, right? So now in order to get it into SHM or any oscillatory motion, we have to displace it slightly. So let's just assume that we displace it anti-clockwise by some distance, or like some angular distance. I've just called it d theta over here. And we know that the arc length can be given by distance times the angular displacement. Here the distance between this and this is 2r. So here the displacement is going to be 2r d theta. And over here it's going to be r d theta. And here it's going to be r by 2 d theta. Right? If you cannot see it very well, so that's how it is. And so basically let's start off with the assumption, not assumption really, but let's just try to calculate the tension that's developed in each string. So when you displace it slightly anti-clockwise, this is gonna happen. Like this is what's gonna happen, right? It's anchored to this point. It's not anchored really, but it's like the oscillations, SHM is gonna take place only when you displace it slightly. If you displace it by a lot, it's gonna start slipping all over and like you're not gonna get SHM. It's gonna be like somewhat chaotic. So in order for it to be oscillatory, it's gonna be small displacements. That's why I've taken d theta. So for the most part, we can just consider this bottom part to be anchored, right? So this is how it's gonna go. Once you displace it anti-clockwise and leave it, it's gonna go like this. And what exactly causes this oscillation or rotation is the torque that's acting because of the tension developed on this string and this string. And that's what we'll be finding. And when you displace it anti-clockwise, the strings to the left are just gonna go slack. They'll just become somewhat like this. When you displace it anti-clockwise, they're just gonna go slack like that. Same thing with this one over here. And so the only thing, but here it's gonna be elongated by some amount, and that's what we need to find out. So we know that this play is gonna get elongated by r d theta, and this is r by 2 d theta. And since both of these are of the same string, the total elongation in string 1, so string 1, the total elongation is going to be r d theta plus r by 2 d theta, which gives 3 by 2 r d theta. And we know that this elongation, you know that the strings are inextensible. Like you have a string, you can't extend it really well. But since it's connected to a spring, the spring is going to be expanding. And whenever the spring expands, some tension is going to be created within it. So that tension can be given by k into x, where here k is basically the coefficient of this. So since we already determined this to be 4k, we can substitute that. So 4k, and x is basically the displacement or elongation, and the elongation is given, we found it out over here, which is 3 by 2 r d theta, right? So that's the tension over here. So tension, and since it's the same string, the tension is gonna get propagated throughout the string. So you're gonna have two tensions pulling it at two different points. And now similarly, we have to find the tension at the top part. And when you displace it anti-clockwise, this part's gonna go slack, and this part's gonna be under tension, and the spring over here is gonna extend by some amount, right? But we know that this is 2 r d theta, and for this part to get elongated by 2 r d theta, you need this part to get elongated by 2 r d theta, and similarly even this part by 2 r d theta. So this string that you see over here, this string that I have highlighted, that string essentially needs to be elongated by 4 r d theta. So the string over here needs to be elongated by 4 r d theta. And when I say string 2 over here, for the time being I mean this string, but later when we come to the string, you can assume that string 2 applies to the other string, but for now it's the string attached to this pulley. So the total elongation is going to be 4 r d theta, because 2 r d theta here, 2 r d theta here. And the tension, let's just denote this by small t. The tension that's going to be developed over here can be given by kx again. And here in the question it's given that the k is 9 by 16k. So 9 over 16k into the elongation, which is 4. Oh yeah, this is meant to be it's, so you basically have k into 4 r d theta. So this is essentially 9 by 4 into k r d theta, right? And since these both are the same string, the tension here is going to be 2t. And like if you notice that this pulley, it's always going to be in like equilibrium, right? Translation equilibrium. So like the tension, the force acting on this part should be equal to the force acting on this part. So over here there's going to be a tension of 2t on the spring. It's going to be in this direction, but tension, so basically you're looking for 2t really, because the tension that's going to be acting on this part is 2t, not t. So 2t is gonna be 9 by 2 k into r d theta, right? So right now we have everything that's important for us to do the torque analysis, and when we do the torque analysis we're gonna get the answer. I mean, not the answer really, we're gonna get the time period for like when it's displaced anti-clockwise. And so basically, if I make some space over here and write, we know that I alpha is basically the net torque acting on it, right? And where I is basically the moment of inertia of the disk, but about which axis? We're not going to consider it through the center. Instead, we're going to consider it at this bottom part, which if you remember through this example, we see that it's mostly stationary, right? So that'll be the appropriate axis. So we can the moment of inertia of the disk itself is going to be mr squared by 2. Since we're displacing it by an r, like the axis of rotation, it's going to be 3 by 2 mr square into alpha is equal to the net torque. And we know that the net torque acting on this is because of 2t on the string at this part and t through the middle, and there's another t at a distance r by 2, right? So what we'll be doing is we'll be summing up the torque. And if you notice real good that all of the torques are acting only in one direction. So when you displace it anti-clockwise, the torques are mainly going to be trying to pull it the opposite way, and that's eventually what even gives you your oscillatory motion. So it goes like this basically. So you're gonna get 2t times 2r, because torque is basically F times L, or like distance or displacement, whatever, distance from which the force acts on, right? Plus T times R plus T times R by 2. And we know 2T is basically 9 by 2 kr d theta times 2r, plus if I take the from here I get 3r by 2 into t, and we know t is 4k into 3 by 2 r d theta. 4k into 3 by 2 r d theta. And right off the bat I can see like a 9 by 2 over here and like a 9 by 2 over here. So let me just take them together. You could probably do the calculation on your own, but this is something that has come to my eyes right now, and I would want to solve it like this. So this is k, by the way. I've taken r square and k d theta common. So what you're left with over here is a 2 plus, similarly I've taken the same things common over here, and there's a 2 over here, a 4 over here, which eventually just gives me a 2. I've taken all of these common, so I'm gonna be having 2 again. So this is eventually just gonna simplify to 4, and 2 4s are, so you're gonna get 9 into 2 r square k d theta, right? So now all of this is equal to your 3 by 2 mr square alpha. R square and r square gets cancelled, and 3. So what's gonna happen is that 3, and you get your alpha as 3 times 2 times 2 into k d theta. 2 2s are 4, so you're gonna get 12k d theta, right? Yeah. So you, instead of writing this, so let's just multiply both sides by r, and the reason is r alpha. What's r alpha? R alpha is basically acceleration, since it's pure rolling, right? So now I can take the one of the 2's and r d theta together, so I get 2 r d theta. And what exactly is 2 r d theta? 2 r d theta is this displacement. So you're gonna get 6k just a second, and let's just call 2r d theta, which is what we eventually displace it by, as x. So we get 6k into x, right? So from this, what we have is here, in fact, for SHM, we know that A is always of the form like kx, right? Where and here basically the 6x is gonna be your omega square, which is your angular velocity for SHM, right? So we get here omega as again, there's a divided by m over here. You bring your m over here, so there's a divided by m, I forgot. So your omega is basically 6k upon m, right? And let me just write this part over here, and you get time period as 2 pi root m over k effective, and k effective over here seems to be like 6k, so you have m over 6k. So this is your time period. But if you notice in the question, yeah, so like the trick in this question lies in the fact that you don't really care about time period, right? I'll tell you why. Because right now we have only displaced it anti-clockwise, and when it's displaced anti-clockwise, it's gonna be under the influence of the springs over here. But as soon as it comes back to its mean position over here and displaces clockwise, it's gonna be under the influence of a new set of springs. So we need to find the time period in both the cases. So notice, this time period is for one entire oscillation, but we know that we only have to consider the time period for half of this, because the other half is going to be different. This part and this part are going to be different. So we essentially need to be considering time period by 2, which is going to be pi by pi root m over 6k. And now we have to deal with the other set of springs. Now we have to take the, I don't know why I created a box, but it's fine. So now we have to consider the fact that it's gonna be displaced in this direction. And again, this part is still gonna be 2r d theta. This is still gonna be r d theta. This is still gonna be r by 2 d theta. But now you have this set of springs over here, right? You only have 2 springs, and from the previous question you got to know that we solved this to be k and this to be k, right? So same thing I've written over here. And when we displace it in this direction, the remaining string over here just slack off. So like there is no tension from their side, right? So this is how we're going to be solving the question. So this is still string 1. So let's write string 1. And we know that it gets displaced by r d theta. If this displaced by r d theta, so should this entire spring, right? But the thing is, this spring, uh, the spring over here gets displaced by 2rd theta. The same reason from the previous question over here. So, but the displacement in this part is going to be 2rd theta, and we know that the tension, let's call this T over here. So the tension that's developed is basically Kx, and here K just remains K, and X is going to be 2rd theta, because if this displaces by rd theta, this entire string over here needs to be displaced by 2rd theta, right? So this is the tension, and similarly the tension propagates to this part of the string, and for this pulley to be in translational equilibrium, there needs to be like a similar force of 2T acting on the side. So what we require is 2T, and we get 4kr d theta, or so you get 4kr d theta, right? And similarly we do the same thing for the top part of the spring. So string 2. So for the second string, the tension is gonna be because of the spring alone. So you're gonna get your displacement is still 2rd theta, and your tension in this case is gonna be K into X, which is K into 2rd theta, which gives you 2krd theta, right? So right now if I draw the free body diagram of the disk, remember you've displaced it in this direction, so there's a tension acting over here, and there's a tension acting 2T over here. So to find the torque that's caused due to this, what we'll be doing is the torque analysis. So we know I alpha is again, so we know from the previous case that it's 3/2 mr square into alpha gives T, and T in this case is just 2krd theta, 2krd theta times 2r plus 4krd theta rd theta times r, which basically gives you, and again just as I mentioned, I would want to take 2r and d theta together, and even this 4 can be broken down into 2 and this rd theta together, right? So you get 2k into 2kr times x plus 2kr times x, which basically just gives you 4kr times x. R square, my bad. Not really, because so now what we can do is we can cancel this r over here and this r over here, so we get 3/2 mr alpha is equal to 4k, and we know r alpha is basically a, right? So we get a is equal to 8kx upon 3m. Is the calculation right? Hold on, this is small. Yeah, seems to be. So right now you have your omega square to be root of 8k upon 3m. So your time period is 2 pi root so you have your time period is So we can simplify this as 2 pi divided by 2 root 3m over 2k, right? So this 2 gets cancelled, and again, even in this case, what we're looking for is t by 2. So your t by 2 is gonna be pi root 3m over 2k, and to find the answer we need to add both of these time periods, and the final answer is just gonna be pi root m over 6k plus pi root 3m over 2k, right? So you can write this as, you can take pi root m over k common, and what you'll be left with is 1 over root 6 plus root 3 upon 2. And simplifying this, you can cancel your root 2 over, you can multiply this by roots, basically pi root m over k times, you multiply both sides by root 3, you're gonna get 3 plus 1, which is 4 divided by root 6, and this can be simplified to root 3 and 2 root 2. So you basically have 2 pi root 2m over 3k. This is your final answer.